So far, most of the example problems we've covered have been examples in which mechanical energy has been conserved. We've been ignoring non-conservative forces. In this example, let's investigate how to calculate for work done by non-conservative force. So let's say we have a block with a mass of 6 kilograms, and it's compressed against a spring with a stiffness of 1,200 newtons per meter. And maybe the spring has been compressed from its natural length a distance of 20 centimeters. Okay, let's make up some more values as well. Let's say that this is 45 centimeters. And then to this other plateau is a height of 75 centimeters. So the figure's not necessarily drawn to scale. And lastly, say the block ultimately reaches this point, and when it does, we measure its speed and find it's traveling at exactly 1 meter per second. Okay, so the question here is, how much thermal energy has been produced in this process? How much mechanical energy has been converted into thermal energy? Remember, we think of energy as coming in two broad forms: useful, harnessable, or what we call mechanical, and wasted, which is generally thermal energy. Mechanical energy can either be kinetic or potential, and you can convert between these two all day long if all you're overcoming are conservative forces. But if there's any non-conservative force, then energy is going to move this way, and it never moves back in the other direction. Okay, so we'll label a point A in our diagram, consider all the energy there, and sure, there's a point B and a point C, we'll call this point D. We don't have to compute the energy at B or C in order to figure out how much mechanical energy was wasted as thermal. We can just compare the energy at the starting point to the energy at the final point. So all the energy at point A and all the energy at point D have to be equal. Okay, so let's choose a wise reference system. Instead of letting height equal 0 down here, why don't we let height equal 0 here? In that regard, then we don't have to account for any gravitational potential energy at point A. In fact, all we would have at point A is elastic potential energy, the energy stored in the spring. Okay, then at point D, we clearly have an object in motion, so there's kinetic energy, and it's higher than the reference level, so there's some gravitational potential energy. If there is any thermal energy developed, it wasn't harnessed at point A. If any thermal energy was developed, it was a byproduct, it was a result. And so by the time the object gets to point D, thermal energy has been developed. So this is not an example of conservation of mechanical energy, but total energy is still conserved as long as we account for the Q value. So how can we state this with more detail? When we say 1/2 kx squared is equal to 1/2 mv squared plus mgh plus q. And so if all we're trying to do is solve for the Q value, we just need to rearrange our equation. The Q value is 1/2 kx squared minus 1/2 mv squared minus mgh. So let's plug in and see what we get. 1/2 times 1,200 newtons per meter times 0.2 meters squared minus 1/2 times 6 kilograms times 1 meter per second quantity squared minus 6 kilograms times 9.8 meters per second squared. Now h. What is h? Well, if this is 45 centimeters and this is 75 centimeters, then the value of h that we have here would be 30 centimeters or 0.3 meter. Sorry, I'm running off the page a little bit here. Okay, let's calculate all this out. Grab a calculator and see what you get. when you multiply 0.2 squared times 1200 times 1/2. Yeah, okay, I get the same thing. 24 joules. Take this piece by piece. You don't need a calculator for this one. 1 squared is obviously 1, and half of 6 gives us 3. Okay. Well, why don't we make life easy on ourselves and make this an example problem where we let g equal 10. After all, this isn't a lab. None of the values given here represent authentic measurement, so we're allowed to round up just to make the math easy. So let's call this 10 meters per second squared instead of 9.8. So this again is mental math, isn't it? 0.3 times 10 would give us 3, and then times 6. Okay, so this would give us 18. So 3 joules and 18 joules is 21, and when we subtract 21 joules from 24 joules, we find a Q value of 3 joules. There we go. Now we should take this a step further and say, what's the coefficient of friction? Now let me add a little more detail to this problem. Let's just make a hypothetical case where every surface is frictionless, no friction here, no friction here, no friction here. Let's say that the rough ground was all here from point B to point C. So all the thermal energy was developed along that path. Okay, so we'll say, for example, that distance is maybe 15 centimeters. Then what's the value of the coefficient of kinetic friction on that portion of the ground? Well, we can think of this Q value as work done by the force of friction, which in turn would be the force of friction multiplied by the displacement. The force of friction is equal to mu times normal force, and if we were to draw a free body diagram, as it slides across that level ground, normal force and mg balance one another out. So we can really say, in this case, Q is equal to mu times mg, in other words, mu times n times d. So the value of mu would be Q divided by mgd, 3 joules divided by 6 kilograms times 10 meters per second squared times 0.15 meter. Okay, grab a calculator and see what you get. Okay, hopefully you get the same thing I got. Mu is 0.33. So there you have it, an example where we have to account for the fact that once in a while mechanical energy is converted into thermal energy.